All right, so as I was saying, we are going to be using our Newman projections to analyze different rotational conformational states of molecules. And in particular, we're going to be looking at different ones and comparing their energies, how stable they are. So again, we're going to start off, we're going to be looking at molecules in our Newman representation a whole bunch. And then we're going to be taking them and thinking about rotating them about this front carbon or maybe even the back carbon. But nonetheless, that's sort of how we're going to be playing with these. Another important concept that sort of will allow you to quantify that rotation is what's called a dihedral angle or a torsional angle. That's going to be the angle between, for example, these carbons here. I'm sorry, these hydrogens here. Notice how this isn't a traditional bond angle because there's actually a bond in between these two hydrogens, right? The one that's between my front carbon and my back carbon that's represented by that circle. So this is what makes it different than a bond angle. This is again called a torsional angle. So it would, in this drawing here, it would be like the angle between this hydrogen and this hydrogen, looking down that carbon-carbon bond. Okay, so by increasing or decreasing this torsional angle, that's effectively the same thing as rotating about that single bond. Okay, and there are going to be two main different types of rotational conformations that we're going to see. There is the staggered conformation, which is pretty much what we've been looking at this whole time, where everything is nice and evenly spaced between the front and back carbon, right? That would be the staggered conformation. Another one we're going to see is the eclipsed conformation. So if I take my staggered and I rotate it by a dihedral angle of 60 degrees, I will arrive at an eclipsed conformation, where now the whole idea is that these guys are actually sort of in parallel with one another. Those bonds are in parallel. Those bonds are in parallel. Although it's not really drawn perfectly with a dihedral angle of 0, because otherwise you wouldn't really be able to see things very easily. This is meant to be a dihedral angle between two hydrogens of 0, or they're sort of exactly parallel with one another. So then which ones do you think, which one do you think would be in general the more stable of these conformations, right? Staggered or eclipsed? So without any sort of information, you could imagine that this staggered is actually lower in energy and the eclipsed is higher in energy because of just, repulsive effects. Electron or electron repulsion between hydrogen atoms, for example, that don't want to be next to each other. In general, things in chemistry like to be as far apart as possible, right? That's the whole VSEPR theory. It actually turns out that there's another really important factor that leads to the stability of the staggered conformation. Like that explanation was all well and good for scientists, except for with things like hydrogen, which are quite small. So it made sense for bulky groups that don't want to run into each other through steric effects. But to explain just how much more stable it was for something like hydrogen was a little confusing until quantum mechanics came around. And this, we talked about it before, we talked about bonding. Two bonding atomic orbitals will come together and they'll make two new molecular orbitals. One of those will be bonding and one of those will be anti-bonding. It turns out that there's this weird phenomenon called hyperconjugation, where the bonding molecular orbital of one atom, right? So this is this carbon-hydrogen bonding orbital here. So that's the bonding. And the anti-bonding molecular orbital of the adjacent carbon. So now I'm talking about this carbon here, and this is its anti-bonding orbital. Turns out that in the staggered conformation, these two can overlap, and that's something that adds to the stability of the staggered conformation, making it that much more favorable. Hyperconjugation is a phenomenon we're going to see come up sort of over and over again. It's cool to think it's absolutely bizarre because it's just rooted in quantum mechanics until you get to the point in your chemistry career where you're running through calculations that prove that this is true. It doesn't really mean much other than to say fancy quantum mechanics leads to the stability of the staggered conformation. Okay, so this is what we're going to do. We're going to be using what are called these energy diagrams to show these rotational conformations, to show what happens as we go about rotating these molecules. And it turns out we're going to be looking at ethane specifically. And as we said, the eclipsed conformations are less stable. Well, how much less stable? So it turns out that two eclipsed hydrogens have a 4 kilojoule per mole penalty over the anti-conformation. So this is less stable than anti. Okay, that's what that means. And so for each of those four, it's going to add this penalty of 4 kilojoules per mole. So what would be the total for having 3 eclipsed hydrogens? That would be a penalty of 12 kilojoules per mole. So let's go ahead and represent that on our potential energy diagram here. So first of all, we're going to start right here. All right, starting in this rotational conformation here. This is, anti, sorry, this is, I didn't even introduce that. Anti is another way of saying staggered. Okay, so I'm going to start off here in my completely staggered conformation, and then I'm going to rotate this dihedral angle by 60 degrees. So first of all, that would give me this conformation here in terms of my Newman projection. You can see that we are rotating this front carbon, this red hydrogen on this front carbon. Actually, let me do this. This red hydrogen on my front carbon is coming down. I'm rotating it. And so what's going to happen to the energy as I do this rotation about the single bond? It's going to increase, right? Because of this penalty that occurs for each of these eclipsed hydrogens. All right, and then I'm going to keep on rotating it. So now following the same front red hydrogen, that's going to come down here. Now I have a new staggered conformation. So the energy drops back down to where it was before. And then I'm going to keep going. Now I have my two red hydrogens that are eclipsed. Here's again my front one. And what's going to happen? Again, the energy is going to increase, and it's going to increase by exactly that 12 kilojoules per mole, right? 4 kilojoules per mole for each of those eclipsed hydrogen bonds, carbon-hydrogen bonds. All right, and then we just keep on going here, following this same hydrogen around. The energy will drop again for my staggered conformation. The energy will rise again for my eclipsed conformation. And then finally, I arrive back where I was before. All right, so this is back to the start. So if it kept on going, I would just repeat through this potential energy diagram here. All right, so notice this is what we call a rotational conformational analysis, right? So we basically just went through and put numbers to what's going to happen as this molecule rotates about this single bond. You can see that what this diagram shows is that this molecule would like to spend most of its time in the staggered conformation. Now, of course, molecules are always moving. Thermal energy is plenty enough to overcome these barriers, so it is still rotating. But if you sort of were able to freeze time and count how much time it's freeze time, go in and look at the conformation, see how much time it spent staggered versus how much time it spent eclipsed, it would spend most of its time in that staggered conformation. All right, so then we can sort of do the same thing, but with a more complicated molecule here. Now we're going to stick a methyl group on there. Okay, so this is now, instead of doing ethane, now we have, what do we call a 1, 2, 3 carbon hydrocarbon? This would be propane. So now let's look at the rotational conformational analysis of propane. So again, the penalty for an eclipsed carbon-hydrogen bond is 4 kilojoules per mole. Well, what about now this methyl group hydrogen strain that we're going to incur? This is going to have a larger penalty of 6 kilojoules per mole. So now I have penalty of 4 for every hydrogen that's eclipsed, but for every methyl hydrogen that's eclipsed, now I have to add a penalty of 6. So again, you sort of start over here in this staggered conformation, start rotating that methyl group down, decreasing that torsional angle there. And now instead of just a penalty of 12 kilojoules per mole for every eclipsed conformation, we incur a penalty of 14 kilojoules per mole for every eclipsed conformation, because that's 4 plus 4 plus 6, right? This is 6 kg per mole. This one's 4, and this one's 4. Okay, so that would be what the rotational conformational analysis of propane would look like. So now we're going to go make things a little bit more complicated, of course, and we're going to replace one of these hydrogens with a methyl group. All right, this is the next molecule we're going to look at. This will be butane, and now you can sort of maybe anticipate what the complication of this is going to be. We have one staggered conformation, so these are all staggered. But our staggered can be broken down into 2 different classes. One of them is the anti, where both of those methyl groups are as far away as possible, right? So anti is where your big bulky groups are far away as possible. And then you have this, it's called a gauche staggered conformation as well. So notice that there are 2 of them. And that is when it is still staggered, but you have those methyl groups sitting next to each other, right? And methyl groups, of course, are big and bulky. This is meant to represent what would happen with any big and bulky group, but this is just a good example here. There's going to be a penalty of 3.8 kilojoules per mole for a gauche conformation over an anti. So these are 3.8 kilojoules per mole less stable than the anti-conformation. So even though these are all staggered, staggered's good, right? That's step 1 in this whole thing. Eclipsed bad, staggered good. But now we have this other fact that if there's this gauche staggered conformation, that also comes with a bit of a penalty of 3.8 kilojoules per mole. Okay, so now let's go through the rotational conformational analysis of butane, starting in this staggered conformation. So again, this is going to be, I'm sorry, anti-conformation. So this is start, and this is my, that's not a good place to put that. This is the anti-conformation. Okay, and then just like before, I'm going to start to rotate this molecule by rotating that front carbon, bringing that methyl group down. I'm going to have this eclipsed conformation. Okay, here I have my hydrogen strain there. The penalty for the hydrogen eclipsed was 4 kilojoules per mole. And the penalty for each methyl hydrogen eclipsed was 6 kilojoules per mole. And I've got 2 of those. Okay, so that means that as I rotate this molecule, the energy increases to a total of 16 kilojoules per mole over my AT conformation. Then I rotate again. I get to my staggered conformation, but now this is, remember what we called this was the I need this space. Remember, these were the gauche conformations. Okay, and although those are more favorable than these eclipsed conformations, they're still going to sit 3.8 kilojoules per mole above that anti, right? So here was the energy of the anti conformation down here, and now I have my gauche sitting up here, 3.8 kilojoules per mole above that. So now I'm going to rotate. Oh, it's too far. Yep, sorry, I'm gonna get rid of stuff. All right, and now the energy increases, and notice that it increases even more to now 19 kilojoules per mole because I have an eclipsed methyl-methyl. Right? Before propane, the only thing you had was an eclipsed methyl hydrogen. Now we have an eclipsed methyl-methyl. This is all tabulated on this table here. You can see that an eclipsed methyl-methyl has a penalty cost of 11 kilojoules per mole. And that's going to be in addition to all of these hydrogen-hydrogen eclipsed penalties, which come at 4 kilojoules per mole. So that's how we get to 19 here. Okay, so then keep going. Notice I still have, I get to another staggered conformation, of course, but now it is still a gauche. So again, it is still sitting that 3.8 kilojoules above my anti-conformation. Keep on rotating, keep on rotating. I get to another one of these states where I have 2 methyl hydrogens, penalty of 6, plus a hydrogen-hydrogen, penalty of 4. So that would be 16 kilojoules above. And then finally, I'll arrive back at my anti-conformation, sitting there at the lowest energy level. Okay, so this is how we sort of diagram out the rotational conformations of a molecule. And this is what the Newman projection is really good for, is picturing these staggered versus eclipsed conformations. Again, this information, this sort of penalty information is all tabulated in this table here. You're going to be using this in your challenge problem this week in order to construct one of those rotational analysis diagrams, okay? So make sure to look through this video again, and if you have any questions, and to especially understand the connection between the table and the graph. Where do the numbers come from? How is this 4 used in that diagram? That's really important. So make sure you review that. Okay, cool.